Hi everybody, we're going to start talking about chapter 6. So I'm going to start with the first 10 or 11 slides where we're going to kind of talk a little bit about light. So it doesn't seem like chemistry would be related to light to a lot of people, but a lot of times what we perceive as distant differences in colors of materials have to do with motion of electrons. So we're going to give you a little background on electromagnetic radiation or light. And the first thing we're going to talk about is the idea that the speed of light is constant across the entire electromagnetic spectrum. So this doesn't matter if we're talking about different colors of visible light, or if we're talking about infrared or ultraviolet light, or even some further reaches of the spectrum. Light, when people first started studying it, was believed to behave just like a wave. But as science advanced, we've come to think of it as having both wave-like and particle-like properties associated with it. So when we talk about waves, these are showing you a picture of light as what we call a transverse wave, which means that it vibrates up and down compared to the direction that it's moving in. So I've drawn an arrow to the right there on what would be the rest position. And so the light is moving to the right, but it's vibrating up and down. That's called a transverse wave. Very similar to if you stood at the ocean and you looked out and you saw waves coming towards you. So there's three main terms that we use, and those are amplitude, wavelength, and frequency. And we're going to be mostly interested in wavelength and frequency. So let me just move my face out of the way here, hopefully. So the wavelength is essentially the distance from peak to peak or crest or trough to trough. And it's measured in meters, and we use this weird looking symbol for wavelength, the that lambda that kind of looks like a let me see if I can grab my pen here for a second. I got it kind of small. So this thing here that I've circled is what we refer to as the wavelength, okay? So it kind of looks like a shepherd's crook. It's measured in meters. Amplitude is the height of the wave. So when I look at from the rest position to the highest point, you could also measure it from the rest position to the lowest point. And frequency, I can't really show on the picture there, but frequency is the number of waves that pass a point per second. And so it's measured, we either use an F or this weird looking V, which is called a nu, in order to represent frequency. And frequency is waves per second. We don't usually show the word waves, so we just give it a 1/seconds, or another unit that's comparable that's exactly the same is a hertz. All right, so this is a picture of the entire electromagnetic spectrum. We're used to thinking about light as just being, light is just part of the electromagnetic spectrum. And this little tiny piece in the middle that they're showing you is being expanded out to show you what all the different colors of visible light are. So you guys all learned this acronym back like in middle school, Roy G. Biv, for red, orange, yellow, green, blue, indigo, violet. Bad news, they gave indigo the slip a while ago, so there's really no indigo anymore. It's just Roy G. Biv now. I think we should leave it in. It seems, it rolls off the tongue a little easier. What you'll see when you look at this is that down at the far end of visible light, where my red is, all right, they're showing me the wavelengths as being about 750 nanometers. And at the other end, where violet is, my wavelength is around 400 nanometers. And as a matter of fact, as you pull that out, that entire scale is set up the same way, so that my wavelength is increasing when I move to the right, and my frequency is increasing as I move to the left. So some other parts there, you see at the higher wavelength end or the lower frequency end of red is infrared light. And to the right of that is microwaves, which you've all experienced before when you use a microwave. And then radio frequencies are the lowest frequency or the longest wavelengths. And so radio frequencies, this isn't what you hear. It's not sound, okay? It's actually the what's broadcast from a radio tower. On the other side, as we move to the left from violet, you see ultraviolet. You've heard about that with the sun, and then X-rays, and then gamma rays. So one of the things you can see real clearly here is that as the wavelengths get bigger, the frequencies get smaller. And you can also see that the different wavelengths or different frequencies of light, we perceive that as changes in color in the visible portion. So there is a relationship between frequency and wavelength, which we're going to talk about in this slide. So I'm just trying to grab the top of this for you there. So the relationship between frequency and wavelength is represented using the equation C equals F lambda, where C is the speed, F is the frequency, and lambda is the wavelength. So as the frequency gets bigger, they have to always multiply out to the speed of light. So then what that means is the wavelength will get smaller. So let's plug into this equation. Let's do a simple calculation. It says, what's the frequency of light associated with a wavelength of 510 nanometers? So I wrote my equation. C is a constant, 3 times 10 to the 8th meters per second. And you notice that I replaced the nano with 10 to the minus 9th because my units have to be the same. If I have meters, if I have meters on one side, I have to have meters on the other side. I keep losing my pen all the time, I'm sorry. So I took, instead of writing nanos, I used 10 to the minus 9 because that's what nano means. So I plugged into the equation and I calculated my frequency. You can see the meters cancel out. And I'm just left with 1 over seconds. I could also call that hertz. I could also say 5.9 times 10 to the 14 hertz if I wanted to. Oop. Didn't mean to do that, guys. All right, so let's take a look at our next slide. So now we're going to talk a little bit about the relationship between frequency and energy. So this says that the amount of energy associated with light at a particular wavelength is directly proportional to the frequency. So this is different than the relationship between frequency and wavelength. Frequency and energy change the same way. So as the frequency goes up, the energy goes up. And so what that means is that light that's red, which is at a lower frequency, doesn't have as much energy as light that's violet, that's at the higher frequency end. So scientists studied this concept, and this is actually what led to the idea or the concept of what we call the particle nature of light. So let's take a look at our next slide, if I can. All right, so one of the things that scientists were able to discover was that light, like when they looked at things that were glowing, like you've heard the expressions red hot or white hot before, and like that. So this is showing you essentially a slide that's got some different pictures of different materials being heated up. And so the wave nature of light doesn't explain why it is that an object that's being heated glows different colors as the temperature increases. Max Planck, who is one of the first scientists who studied this, explained this by assuming that energy comes in discrete packets that he referred to as quanta. So Max Planck worked with a man that you've probably heard of before, whose name is Albert Einstein. And they carried out some experiments to try and understand what was going on with light and the frequency of light, like that. So this is kind of a little bit off, but in 1905, essentially, Einstein used Planck's theory to describe what's referred to as the photoelectric effect. And what he was looking at was what happened as different types of light struck the surface of different metals, and what kinds of light they observed that different types of light were able to create what we call a photocurrent, or a current that's used to due to the light striking the surface. So for each metal, what they found was that light of some specific minimum frequency was required in order to cause the effect. And that the amount of energy associated with that light could be calculated based on the frequency of the light and an equation that Maxwell Planck had come up with that related energy to frequency. So the minimum amount of energy that's required to emit an electron from the surface of a metal is referred to as ionization energy. And these are values that are relatively well known. So what we're going to do is we're going to look at what Planck and Einstein did, essentially. They used this idea of different amounts of energy required to kick off an electron in order to calculate the minimum frequency of light that was needed to accomplish that. So if I know the wavelength of light, I can calculate the energy in a packet or a photon, essentially, of that particular light. So these two equations at the bottom, when you look at them, say that C is equal to the wavelength times the frequency, and that the energy is equal to Planck's constant times the frequency. So H is what we call Planck's constant. So H has a value of 6.63 times 10 to the minus 34, and its units are joule seconds. All right. So if I know the frequency of or the wavelength of light, I can calculate its frequency using the top equation. And if I know the frequency, I can calculate the energy that's associated with that particular frequency of light. So the idea here is that the light behaves like a small packet. All right, so we're thinking of it now, instead of behaving like a wave, we're thinking of it as behaving like a particle. And that packet is capable of interacting with matter at the molecular level. So essentially, if I want to kick an electron off the surface of a metal, I need one of these little packets, we refer to those as photons. I need one of these little packets in order to accomplish that. So the E that you see in this equation, where we look at E is equal to H times the frequency, that E is the energy that's with one tiny packet. The idea is that light can be transferred in these little packets and then can interact with matter. So this is a calculation that we're looking at. So I've written at the very top here, 1 photon, 1 atom. So this is telling me that potassium has an ionization energy of 222 kilojoules per mole. And what we're going to do is we're going to calculate the minimum frequency of light that I would need in order to eject an electron from the surface of a potassium atom. So I wrote the equation that K is equal to K plus 1 electron. So I wrote the equation that K is equal to K plus 1 electron. You can see that over here. All right. And then I'm going to use the equation E equals HF in order to calculate the frequency. So I know the energy. It's 222 kilojoules per mole. The problem is that that equation, the E equals HF, that only works when I'm talking about the energy associated with a single photon. And it's 1 photon per atom. So I have to convert my energy. Instead of being joules per mole, it needs to be joules per atom. So I took my 222 kilojoules per mole, multiplied by 1,000 joules per kilojoule, and then I divided by the number of atoms in a mole. And I came up with 3.69 times 10 to the minus 19 joules. Now, I took that number and plugged it back into my equation. I used Planck's constant for H, and I solved for the frequency, and I get 5.55 times 10 to the 14th per seconds. So I'm gonna leave off there, and then we'll talk about we'll talk a little bit more about what happens here and how we relate light essentially to the motion of electrons around atoms.